All right, so in this video, we're going to take a look at some of the bisectors of a triangle. So you should have a sheet of paper. If you have your notes page, if you don't have your notes pages, you can just take any sheet of paper and you're going to fold this paper in half short ways, which we like to call hamburger in class. So you can see I put a dotted line here, so you can see I've turned it long ways and I'm folding it in half. And at what angle is this fold? If we look at the fold, well, if we look directly down, it should be going straight across the paper. It should be going at any kind of diagonal from top to bottom straight down. This should be at a 90-degree angle, as long as you matched corner to corner when you folded. So then use a ruler to measure the distance from the fold to each corner of one side. Now, depending on the paper you use, you may get a different distance than me, but when I measured, so you can see my 90-degree angle here. So when I measured the bottom here, you can see kind of the very bottom edge of the ruler there. It got cut off a little bit. It's 5.5 inches. Now, again, you may have a different size paper than me, but make sure you line up the 0 on the edge of the ruler, and measure to the center, okay? Because measure to the corner of one side from the fold, or from the corner to the fold. And then I want you to measure, let's see, the other side here. So same thing. So from the fold to the corner. Now, you should hopefully notice that they are the same length. If they're not the same length, that means you did not fold it directly in half. Hopefully we understand that, if we fold it in half, then we should have two equal lengths here. So now what we're going to do is we're going to take the ruler and we're going to measure from the corner to the top of the fold. So from the corner to the top of the fold, just like this. We're going to place it, and we're going to see how long is this. Now mine is 10 1/16, so that's how long mine is. Again, depending on the piece of paper you're using, might be slightly different. That's okay. So if I measure the other one, I'm going to get the exact same measurement. Okay, so that's what we should notice about this. The measurements are the same. So we've created these equal distances. Both the measurements from the top of the fold to the bottom corners are 10 1/16 inches. And this theorem represents the perpendicular bisector theorem. So perpendicular means 90, bisector means to cut in half. So that's exactly what we did. We drew a line that was perpendicular and it cut the paper in half. Okay, so it's a perpendicular bisector. And what it does is it creates two lines. It's equidistant from the any point on this line. Okay, so I could even start somewhere else up on the line. If I measured from, say, this point where my pointer is down to the corner, it would be the same distance from those corners. So it's equidistant from the lines, right? It doesn't matter where I measure from this line, they will be the same distance. All right, so now we're going to do something slightly different. We have another triangle here, so this should be on another sheet of paper. If you don't have your notes pages, you could hold a piece of paper up here and trace this triangle really quick if you needed to. Fold the triangle vertex to vertex on all three sides, creating perpendicular bisectors for each side. So what this is going to do is it's going to use that perpendicular bisector we just learned about, and we're going to see what it does in a triangle when we do it to all three sides. So if I take this corner and I fold it down, I did the bottom corner first, so corner to corner, and it folds it in half, corner to corner, folding in half, and then again, corner to corner, and it folds it in half. Okay, so I'm folding the triangle kind of in half 3 times, but you notice this line is going off, it's not going through the vertex here. That's not what I'm worried about. I want to make sure I go corner to corner, and then I'll do corner to corner. I'm just folding that paper in half. So note, if the sides are not lined up, it will not be a perpendicular bisector. So also don't worry if it does not go through the opposite vertex. Again, that depends on the type of triangle that we have here. So from the point at which the perpendicular bisector intersects, right here in the middle, measure the distance to the vertex. So I want us to measure from where it intersected. Okay, so you notice I got rid of all those extra lines. I'm just focusing on that spot where it goes through here. So I kind of got rid of all those extra lines just so that we could see. I just want this measurement here. So if I measure these 3 lines from here to the vertex, I should have exactly the same distance on all 3. So what it does is it gives me this central point, which lets me have this measurement that's the same for each one. So it's from that where the perpendicular bisectors intersect, that from that point to the vertex is equal. And that point is called the circumcenter. Okay, so we just did a couple of things just to kind of help us figure these things out, kind of see them. So now we're going to look at the perpendicular bisector theorem. So if a point is on the perpendicular bisector, remember that's that line when we folded the paper in half, then it is equidistant from the endpoints of the segment. Remember, we measured that. We had 5.5 on the bottoms, and then I had 10 and 1/16 going from the very top down, but you can measure it from any point on the perpendicular bisector, and you will get equidistant lines. So you can see PM is perpendicular to AM, so AM is going to be congruent to MB, the bottoms, and then you'd also have PA is going to be equidistant to PB. So you can see the markings here. And the tab, when I tab it like this, 1 to 1, that means that those are congruent. And then 2 tabs or tick marks means that those are equal. They're kind of corresponding to each other. So circumcenter theorem, remember that uses the perpendicular bisector. That was the second little explanation we did where we folded the triangle corner to corner 3 times. So we have the perpendicular bisector of a triangle intersected a point called the circumcenter, right? That was that point in the middle. And that is equidistant from the vertices of the triangle. So you can see the red lines are all the equidistant. They're all the same. And we find that with the perpendicular bisectors. So if G is the circumcenter of ABC, then GB is going to be equal to GA, which is going to be equal to GC, which is just all of these lengths. Okay, so let's actually do a problem. Let's see where this is. So using the circumcenter of a triangle to find segment lengths. So consider triangle GHJ in the figure below. The perpendicular bisectors of its sides are KN, LN, and MN, so we don't have to draw them. They already drew them for us. They meet at a single point N. In other words, N is the circumcenter of triangle GHJ, so that's why we learned about perpendicular bisector and circumcenter together, because we're going to apply it now. Okay, so suppose that LN is 34. Oh, perpendicular bisector really quick. I'm just showing you that all of these are equal. So you can see going around, if these are equidistant from the perpendicular bisector here, this is a different perpendicular bisector, so these ones are going to be equidistant. Well, if this one is equal to this one over here, then it's equal to this one over here, which is the same. So that's kind of why it ends up going all the way around. Okay. So this is just noting the perpendicular bisector so far. And the blue lines, those are 1 tick mark each. Those are all congruent. And the 2 lines that are green, or the 2 tick marks, those are all congruent. Okay. So now we're going to go through and we're going to mark our pieces. So LN is 48. GJ is 80. GN is 102. And they want us to find HN, LJ, and JK. GK. So we're going to go through and we're going to take a look at some of the pieces here. So HN, if you notice, I've already filled it in because HN is one of the green lines here, right? We've already marked that. If I know that one is 102, then each and every one of them is 102. So I didn't have to do any math on that one. I just had to apply the theory here. It's from the circumcenter to the vertex, which makes it equidistant. So since we had one of them, we have all 3 of them. All right. So now we're going to look at GK, and that's half of GJ, right? So GJ, remember it's cut in half here. This is perpendicular bisector, meaning it's cutting this in half. So this section is equal to this section. Well, if I know the whole thing is 80, I'm just going to do half of 80, which is 40. So GK is 40 and KJ is 40. Either one they asked me for would have been 40. All right, on the very last one, we have LJ. So we are going to use Pythagorean theorem here. The reason is, if you look at LJ here, I know that this length here, this green one, that's 102. And I know that NL is 48. But I don't know anything about this section here. Now, I know the bottom is 80 and 40. I do not know that the side has anything to do with 80 and 40. Okay, The different sides do not have to have the same exact measurement. I should have marked this a little differently because the blues aren't actually congruent. They should have different either colors or different tick marks. The two bottoms are congruent, the two left side are congruent, and the two right side are congruent. Kind of misspoke earlier when I said all the blues are congruent, because that doesn't necessarily transfer. It could, if it's what we call a regular triangle, meaning that all the sides were exactly the same, but they didn't tell us that, okay? So just be careful. Don't just jump in and say, oh, it's 40 because the other one was 40. We're going to use Pythagorean theorem because this is a right triangle. So I can do a squared plus b squared equals c squared. Okay, so a and b, those are the legs. Those are the two rays that make the 90 degree. And c is always the one across from the 90, the longest side. Okay, so a squared I just decided was the blue one. B I decided was the pink one. Okay, or B, I'm sorry, I decided was the pink one. And then 102, that is the longest side. It's across from the 90, so I know that's the C. So I have a squared plus 48 squared equals 102 squared. So now I'm going to square my pieces. So 48 squared is 2,304. 102 squared is 10,404. So now I'm going to subtract 2,304 from both sides because I want to get a squared by itself. So I'm going to subtract. So I have a squared equals 8,100. Just 8,100. Sorry, I was going to add more to that. So now I need to take the square root of both sides. So if you weren't sure right off the bat, this one is a little easier to me. I kind of ignored the zeros for a minute. I know the square root of 81 is 9. So the square root of 8,100 is 90. Because I would just, take that down by another 100. But you can always use your calculator and click the square root button if you weren't sure on that one. So that is how we use a perpendicular bisector and the circumcenter of a triangle. I hope that helped, and I will see you in the next video.